will announce that our next speaker is Vladimir Bazhanov, and he will tell us about scaling limit of the six-vertex model and two-dimensional black holes.
Well, it's a pleasure to give a talk on this conference. The work I'm going to talk is a long project joined with Sergei Lukyanov from Rutgers University, Gleb Katausov, currently in Bethe, Hamburg, and Sergei Koval. My talk will be consisting of two parts. First, I'll tell you something about solvable lattice model, in particular spin chains, XXZ chains. And it won't be like it won't be detailed explanation. I just go through some main point, and I hope that many of you have heard about lattice models. So I just try to put the emphasis on what we have been talking about, and we'll be talking about spin chains, in particular XXZ spin chain and its generalization. Briefly mention numerical calculation. That was a huge effort by us to do massive numerical calculation for these spin chains. So briefly mention the Bethe ansatz. So these models are exactly solvable, and so they're solvable by Bethe ansatz and its relation to the spectral theory of ordinary differential equations. When we discuss the scaling limit, so why do we need to study this lattice model? We want to understand what is happening when the system becomes very large. So the number of atoms goes to Avogadro number, and so that's called scaling limit. And so we'll be talking about particular system at criticality, where one can observe universality in conformal invariance in the scaling limit. And the next part of the talk is the black hole story. So not the black holes in 3 dimensions, 4 dimensions yet, but in 2 dimensions. And we'll be talking about Euclidean and Lorentzian black hole, the way to understand the field theory, modular invariant partition functions. And quite surprisingly, there are connections between lattice models and the black holes in 2 dimensions. So what I'm trying to teach you, so we don't need to build expensive LIGO, or how do you call it, interferometers. So we can get the black holes not even in the lab, on the paper. So as a scaling limit of the XXZ spin chain. That's really remarkable. So let me briefly remind what is the XXZ spin chain. So you have a line on spin of spins, spin 1/2, sigma XYZ are Pauli matrices, and we have L, total L sides, and at each sides the 2x2 space. And so that's the Hamiltonian. Only nearest neighbor interact, and the coupling constants here are the same, and here is a different. That's why it's called XXZ, 2 the same and Z is different. So, and we'll be considering the case delta between 0 and 1. In this case, there are long range order, and the scaling limit will get conformal invariance. So one thing to mention is boundary condition. Well, for example, twisted boundary condition, the K is a parameter. And well, that model is exactly solvable. There is a technique called Bethe ansatz, which allows to reduce diagonalization problem for the Hamiltonian, which is 2 to the L by 2 to the L matrix to the solution of L-coupled algebraic equations. Okay, so in the case of one-dimensional critical systems, the conformal invariant predicts that low living energy part of the spectrum has so-called tau structure. So if you take the eigenvalue of the Hamiltonian, so and the limit of the large length of the chain, it has bulk part, and which is not universal. It depends on normalization and finite size correction. And that part is universal. So it's controlled by conformal field theory, and C is called the central charge, and D is the scaling dimension, and N and N bar are two numbers, because that's why it is called tau. It grows up. Starting from D, you have two numbers which control. So, and I'll tell you the answer. If you do this analysis for XXZ model, you'll get a quantum field theory, or rather conformal field theory, of a free massless bosonic field, compactified on the circle. And compactified field has a discrete spectrum of conformal dimensions. And well, it's somehow natural for me, at least. We started with finite dimensional discrete state of spin states, and got a compact field with discrete spectrum. So, and my intuition was, and probably many of people have the intuition, if you start with the spin system, you'll get something at the end, and the scaling limit, you get something with discrete spectrum. And it was a surprise when Jacobsen and Saleur observed that the critical behavior of alternating spin chain, which is built with the same material, but it now has, it's also exactly solvable Hamiltonian, so, but it has next to nearest neighbor interaction. Okay, but it is a reality for XXZ chain. It has the same integrability structure. So that's the first thing, surprising thing. Even we start with finite dimensional state of spins, at the end of the day, we can get continuous spectrum. Okay. So I'll just briefly go through the integrability of this model. It's so that's the transfer matrix, which is six-vertex model. So that's the usual R matrix of the six-vertex model. And the beta is the rapidity parameter, and it alternates for the standard homogeneous chain. We have beta, beta, beta everywhere, and here we have special alternation, beta and minus I pi on 2. And the I pi is the period. Here, somehow is the period of this trigonometric function, so it's a special choice, but it's not necessarily to have I pi. So, and all the machinery of Baxter integrability work for this case. To calculate the eigenvalues of the Hamiltonian, you need to solve these equations for some unknown beta j, m in total, which is less than L. Okay, so that's a coupled algebraic equations. So once you solve that, you can calculate energy whatever you want, but you need to find all solutions. There are many solutions, 2 to the power L, where, and actually here L now is a half of the length, to the power of 2L. and you find whatever you need. In particular, there is an interesting operator which looks like six-vertex model on the square, homogeneous six-vertex model on the diagonal square lattice. So the square lattice rotated by 45 degrees. And so it's expressed for the transfer matrix. So it's belongs to the same commuting family. And what we see that operator, for some reason, has a continuous spectrum. Okay, what we did? So we took the Hamiltonian, which is a sparse matrix, and applied Krylov method for diagonalization. What is Krylov method? Is very simple. So there is an important generalization by Arnoldi, and it's sometimes known as Krylov-Arnoldi method. So if you have a matrix, you take arbitrary arbitrary vector and multiply it by the matrix, multiply again by the matrix, and so on. And if you do it many times, what you get here will be largest eigenvalue. Well, it's easy to understand, but that's the idea, the main idea. We took unprecedented length of the chain, is 24 sides. And the Hamiltonian is approximately 3 million by 3 million matrix. But it's sparse matrix, and it's we can calculate low energy eigenvectors in the vicinity of the ground state. That's what we need to understand universality and conformal invariance. And so we calculate all of them. Okay. So once we know eigenvectors, numerically, we can diagonalize what is called Baxter-Q operator, whose zeros, eigenvalues, allow to extract these solutions of the Bethe ansatz equation without solving the equations. So with our numerical procedure, we got everything from numerical calculation. So, and what particular, there are many states, and the vacuum states look like this. You have the roots beta lie on the real axis, and while on the shifted by imaginary I pi on 2, and there's the same. Okay, so that's the vacuum state. But there are many solutions which look like this. The roots are on these two axes, but the number of roots on the top or at the bottom is more than on the other line. So, and the observation of Saleur, Jacobsen, and Ikhlef was that for these states, the eigenvalue of this quasi-shift operator, which we denote by S, we take the logarithm, multiply by some factor, and in the limit when L length of the chain goes to infinity, it become continuous. Because M is any integer, log L goes to infinity, you can get any limit as you want. Okay. So we found the quantity in the system, which in the limit of large length has a continuous spectrum. So actually that wouldn't be somehow remarkable if this number doesn't enter until this number enter into energy. So that's a finite size correction. That's the bulk part. That's the universal part. it's written in here. The central charge of our system is 2, so that's the central charge part here. And we have two conformal algebra, left and right. And so this delta is the conformal dimension. And for low energy states, it's given by this formula, P, and the number P is quantized. That's the discrete spectrum, which was in the homogeneous XXZ model. But a new quantity S, which appear, enter into the spectrum, and making the this delta and energy having taking continuous weights. Okay. So I skipped the integrability structure of the model and only note that it is related to quantization of so-called IKNS integrable hierarchy. And so, and the algebra of conformal symmetry is the direct product of two, what is called W infinity algebras, left and right. And one fact I want just to mention. So in analyzing the structure of the solution of the Bethe ansatz equation in the scaling limit, it's important to so there is a connection to the spectral theory of differential equation and so somehow these roots we get in the as a solution of the Bethe ansatz equation in the scaling limit become energy level of some Schrodinger equation. That's completely unexpected. But once we establish that connection, we can use spectral theory of the differential equation to analyze the solution of the Bethe ansatz equation. So that's the equation. That's a confluent hypergeometric equation, which is relevant to the vacuum state. And for all other states, you modify the potential here. You add some singular terms with monodromy-free singular points. And so for every eigenvalue of the Hamiltonian, there is some very complicated potential, which we call monster potential. Okay, so that's a brief comment. So that apart from the Bethe ansatz traditional technique, we use some new technique, which is based on the connection to the differential equations. Okay, so that's the formula which Saleur and company observed. And it resembles a quantization condition of quantum mechanical particle in the potential well of the length proportional to the logarithm L. So, and the idea you can, well, make like in a quantum mechanics, you can make it this formula more accurate if it is quantization condition of something by adding the scattering phase. So that's the scattering phase. And what Ikhlef, Jacobsen, and Saleur observed that the quantization condition is very work very well with this formula. Okay, so I'll tell you where they got this formula, but they made a lot of numerical calculation to confirm that it is true. Okay. Not only that we have continuous spectrum in this model, we got a strange formula out of blue. And it has a very good connection with numerical calculation. Okay, so once we got that, believe that it is quantization condition, we can calculate the density of states. So we just differentiate. So when m goes to infinity, we take two successive values of m, and we can estimate the number of states because its solution corresponds to a state. They are called primary states. And so that's just the differentiation of the formula for the phase shift. Okay, so because of factorized symmetry algebra, the states in the scaling limit got a factorized structure. And so in conformal theory, the Hilbert space will be superposition of direct product of Fock spaces. F is a Fock space. So, but as I told you, there is a tau structure. These Fock spaces characterized by the level of conformal algebra. And so, and it turns out that the whole space of state is not a direct integral of the product of undeformed Fock modules. So even if you know the density of the primary state, it is not just you take the Verma modules, a reducible representation of conformal algebra, add them up. So that formula is wrong. Okay, what is right? So the density of this so-called descendant states on a higher level of the conformal algebra. So these two numbers, n and n bar. For n equals 0 is the vacuum. And so, so you need to modify the formula for the density of states for higher levels. And so we got this using the connection to the theory of differential equation. We were able to calculate these densities for all low living states analytically and compared it with numerical calculations. That's the result of numerical calculations. So the red dot is analytic prediction, and blue crosses is the result of numerical calculations. So that's a perfect agreement. And that's for the level 0 and level 1 state, those who belong to these 400 low living eigenvalues. So that's the end of the story about lattice models. So, so what's the story? End of the story about lattice model. Now we come to the next part. So, so we'll be talking about black holes. So what is a, well, black hole is the theory of gravity. Okay, so it's formulated in our word space, which is pseudo or non-Riemannian space, because we have Lorentz metric is non-positive definite metric in our space. Space is, around us is non-Riemannian. But what about the target space? Target space is where the fields, our fields, live. In general relativity, the fields are component of the metric tensor, and of course they live in non-Riemannian space with the same signature as our word. So if you take, say, quantum field theory of the scalar field, or a scalar field, is the perfect is the Riemannian space, even on a circle or on a sphere. So when the target space is Riemannian manifold, we probably shouldn't expect the problem what is called problem with unitarity. But if our fields, our dynamical variables, belong to non-Riemannian manifold, so the first question which arises is about unitarity of theory. So do we have examples? Yes. For example, quantum electrodynamics. So the electromagnetic potential is the vector in pseudo Euclidean space and has a metric signature 1 minus 1. So potentially we do have problem with unitarity. And actually, maybe some of you know that that was a problem long ago. So when electromagnetic field was first quantized, we could do it only in the Coulomb gauge. The divergence of E electric field is 0. But obviously, this is not Lorentz invariant condition. So, but if you want to put some Lorentz invariant gauge condition, when you get a problem. So the resolution was that the gauge condition should only satisfy it, not in operator sense, but in the green functions. So what I'm saying that it is a problem. It was solved for gauge theories, for some other theories, but it is not solved in general. So, and the the black hole, if we want to talk about the black hole, the target space is non-Riemannian. So that's an example of two-dimensional target space, field U and V with the metric, and that is a diagram here with various regions. So the U and V equals 0, these two lines, coordinate line is called horizon, and these zigzag lines is coordinate singularity, where the metric become infinite. Okay? So the time is, the killing vector is time-like in this region. So we, sorry, in this region. 1 and 3, and here it's space-like. So, well, this diagram resemble the Kruskal-Zener coordinates in general relativity for the black hole. Okay, so we actually don't understand what to do with the Lorentzian. I call that Lorentz black hole. And we try to do what is called weak rotation, to replace, consider the case when U star complex conjugation is -3. So when we drop the over sign in this metric, and what is called what we obtain is called Euclidean black hole in 2 dimensions. So the trick is similar what Hartle and Hawking did when they were treating Hawking radiation. So it's not really possible to write down the density matrix of the black hole without this analytic continuation. So what we have, so that manifold, Euclidean manifold, could be visualized in 3-dimensional space. And so it looks like an infinite cigar. The surface, it's two-dimensional surface, the surface of the cigar with the tip here, u equals 0. And when we go far away, the matrix becomes flat. So it's a flat cylinder. Okay. So, and that's, I'll tell you where Ikhlef, Jacobsen, and Saleur got the formula for the phase shift. So they had they have an interesting idea that the spectrum of the this alternative x alternating XXZ chain is governed by the SL2R/U1 black hole sigma model. That's exactly this model. Okay, so and they got a formula from Maldacena, Aguri, and Sun, and compared that formula with the numerical calculation and got an excellent agreement. So, and that is something remarkable. So, if you have this action, so that now x is the worldsheet coordinates. So we, what you can do, you can define what is called modularly invariant partition function. Okay, so you replace your worldsheet by a two-dimensional torus with the modulus tau. So when the partition function will only depend on the modulus, and so, and by construction, it will obey the modular invariance. So that's called modular invariant partition function in conformal field theory. That is a conformal field theory. So one technical problem we need to deal with is that this partition function contains a divergence which arises from geometry of the target manifold. So the tip is located here, but when you go you get infinite. It's unbounded. So we got infinite cylinder, which give a singular contribution to the because of zero modes, basically singular contribution to the partition function. So we need to somehow regularize the partition function. So there are two directions around the cylinder, which is compact direction, and the other direction is not compact. So if you take the somehow manage to cut the cylinder, make it a length of logarithm 1 over epsilon, where epsilon is a small parameter, when the singularity will be 1 over epsilon, so that's logarithm. So the singular term which go here. So that's a partition function of the non-compact Bethe field, and that is partition function of the compact field. So this one, because somehow that's a singularity structure. So that's the no problem. The all problem is here. Okay, so if you understand how to regularize, they got the expression. So they got the expression for this partition function. It depends on tau, but it's infinite sum by two integers and the integral of some two-dimensional integral, so just ordinary integral, not functional integral, over this parallelogram, tau, we have tau here, and we cut a circle in the middle, which is regularization. Because of this phase function in denominator, it diverges. So
sorry, Vladimir, there's just 5 minutes left.
Okay, that's fine. So, and you know, somehow to regularize, you need to cut this cigar, make it finite, and when the modes of the Bethe field in this direction, non-compact field, will be quantized. And so they managed to calculate this quantization condition. So I won't go into it. So it basically, you can form a wave which is go here to the tip of the cigar, reflect back here, that give one phase shift. And here they made a cutoff, which is called Liouville cutoff, which I'm not going to explain what is it. So, as a result, that the Maldacena, Aguri, and San got their formula from this calculation. So the one question is, in spite of numerical evidence, that the Saleur and company proposal is not very satisfactory because Euclidean black hole theory is unitary theory. But the spin chain we considered is non-Hermitian. So that means even we do not deny the connection, we suggest that might be the spin chain is related to Lorentzian black hole. Okay, so I skipped this point, and so let me go from Maldacena, Aguri, and San assumption. They got the assumption that the density of states doesn't depend on the level, and so they got the partition function. Partition function actually, the spectrum of the model contains some discrete states which are like motion around the tip here. So it's continuous and discrete. If you do all this, substitute into the formula and do what Maldacena and Koth suggested, that expression failed to reproduce numerical results. So we substitute the formula, calculate it numerically, this integral numerically gives different answer. So what is right? You need to vary the level, the density of states depending on the level, as written here, and took more complicated density of states, which depend on the level of the eigenvector of the vectors, and that's exactly what we got by studying the alternating six-vertex model. Okay, so that illustration, the numerical calculation, we give, that's a lattice calculation, discrete, continuous, their sum, and that is quantum field theory expression, Maldacena, Aguri, San, their formula, and so the perfect agreement, which we believe is true. Okay, so we can have compared numerically Euclidean black hole. There's a factor of 2 from the lattice model. And we were able to obtain this result because we intensively used what's so-called ODE IQFT correspondence. So, summary of the result. The scaling limit of the spin chain governed by the Euclidean 2D black hole nonlinear sigma model. They are conjectured by Ikhlef, Jacobsen, and Saleur is not right. But a subset of this conjecture, though they didn't formulate it explicitly, that the partition function, which is much weaker, will coincide, is correct. Density of states proposed by Maldaceri, Agoni, and Sun is not correct. So what is left is our proposal for pseudo-Hilbert space of Lorentz two-dimensional black hole and its identification with alternative XXZ chain. So we have to work a little bit on this. Thank you very much.
Thank you, Vladimir. Are there any questions?
Thanks for your talk. I'll ask a question. So I understood you used the Ikhlef method to compute lots of low-lying states, but you also said there is a formula for the eigenstates, which is an explicit algebraic formula. So would it not be simpler to use the algebraic formula to compute the spectrum?
No, for algebraic formula, you need to solve the Bethe ansatz equation. That's the problem. So nobody knows how to solve Bethe ansatz equation in somehow civilized manner. That's the problem. Okay. So people do obtain some solutions. You know, it's well, especially on this case. So for homogeneous spin chains, they are the pattern of zeros is more or less civilized. But for this case, and relatively small length of the chain, you can't just predict. And without knowledge of the pattern, roughly you need to know, to solve the Bethe ansatz equation, you need to know where the roots are. Okay? Because if you try to solve them numerically by starting with the wrong value, they are attraction point. You'll be getting the same solution. That's the problem. No, nobody can solve the Bethe ansatz equation, believe me, except for some particular.
All right, thanks.
Could I ask a question? It's a very naive question, really. The comment you made at the end is that these are unreachable by traditional methods for studying statistical systems at criticality. But a very long time ago, when I was a baby mathematician, I learned about how the scaling limit of Ising models and so on leads you to expansions of correlation functions, which are given in terms of Painlevé functions. Was that not a critical limit? Or is that, am I misunderstanding?
Painlevé convection is even, in some cases, even more powerful. So I was not talking about correlation functions yet.
Okay.
So the Painlevé, but it's applied to some specific system, like Ising model or Ising model.
I see.
As you, and so there are limit to Painlevé picture. So,
right.
Well,
so the reason I ask is because the ODE IQFT or IFT correspondence is also based on the Painlevé picture, right?
No.
I mean, a lot of the
no.
examples.
Thank you for mentioning this, but I can clarify.
Okay, good.
There are functional equations in solvable lattice model. So that's a trademark of Baxter functional equations and so on. And the Bethe ansatz equation, which I showed, is just the condition so that some function is entire function. So if you require what is called Baxter Q operator, so its eigenvalue are entire functions, and you put that condition, and you immediately got Bethe ansatz equation from the functional equation. Okay. So the functional equation contains everything. So the functional equation, you have transfer matrix, which is associated with some representation of affine algebra in our case. Okay. So there are different representations, different transfer matrices, they are connected. And the theory of the connection I am talking, in the theory of ordinary differential equation, you got what is called Stokes phenomenon,
Yes.
or connection coefficients.
Yes.
And it happened that there's a special class of equations, differential equations, second order, or for more complicated systems, third order, and so on, where the Stokes multipliers and connection coefficients satisfy functional equation. And these functional equations are exactly the same. That's those appeared, no Bonlevier, no other properties required. We just study the monodromy group, connection coefficients, and the differential equation which arise. I mentioned this monster potential. So for simple state, it's like maybe Riemann equation or confluent hypergeometric equation. But for excited states, it is equation with apparent singularities, where the solution still continue, the monodromy group remain the same. The potential coefficient have additional singularities, but all solutions are entire functions or meromorphic functions. So there are no additional branch point introduced. So, and that's really powerful. So that something like WKB approximation for, if we know differential equation and use WKB approximation, we can get something which is unthinkable to get from lattice models. So that's very powerful.
When you talk about functional equations for connection coefficients, is that like a monodromy surface, the equation that defines the monodromy surface? When you have Stokes phenomena and you have maybe some other regular singular points, all giving you information about, say, the solutions of a second order system, then all of the data that you get, they are underdetermined.
No, I can
overdetermined, I don't know which. And so you may have, for example, 10 Stokes entries in Stokes matrices, and then another 2 around a regular singular point, and they all are related to each other because they're describing two degrees of freedom. So you come down to a cascade of equations between them, which gives you one condition, and that condition defines a surface.
I think it's a little bit more, it's different, and maybe it's somehow simple. Let me answer your question. Yeah, so that's a differential equation. So it has 2 singular points, a regular singular point at 0 and essential singularity at infinity.
Yes.
Okay? So you have a unique solution which decays at infinity along the real axis.
Yes.
Okay. So because it's growing, so a unique solution. So, but at 0, you have 2 linear independent solutions.
That's right. Yes.
Okay. So you can expand this solution into the basis of 2 regular solutions.
Yes.
Okay. So now you see the equation has symmetry. You multiply x by the nth root of or some kind of
yes. I know what you mean.
Okay. And so the coefficients slightly change.
Yes.
And that relation which we have, they also change. Okay. But you did it, say, 2 times. Okay, but only two solutions are independent here.
Yes,
And here you got three
yes.
at infinity applying this symmetry. And they will be related.
Yeah, I think it's similar to what I'm saying. But in my context, when you're at infinity, you have sectors of validity for the solution, not just on the real line. You have many different sectors depending on what n is. When you go from one sector to a neighboring sector, you get a Stokes relation, a Stokes jump between the solutions. And so you get these free parameters that are related to the free parameters in the adjacent sectors. So you get a whole collection of relations.
I understand. So the point of this calculation, which I tried to describe, but it is hard to describe, that we got not only the leading part, but the correction part automatically. So where the Stokes phenomenon happened after second rotation, okay, we got the leading part and subleading part as well.
Sure, sure. I'm not questioning that. All I'm talking about is the functional equation.
Yes.
And I suggest that that's the same thing as something that describes monodromy surfaces from my side of that, that conversation. And so it's interesting to see that it's coming up as an important issue here. Thank you. I'll take the opportunity here now to thank everybody for coming to this workshop, and especially to the speakers and the poster presenters for being so wonderful with the quality of all their presentations. Thank you very much, everyone.